Hello.
Так, для особо внимательных я небольшое
Now,
уточнение
for the
внесу, потому что
particularly
презентация
attentive,
называется не так, как
I
вы
should
видели
say
программу.
that the name of the
На самом
presentation is
деле
in
мы
fact different from what you
буквально
see in the
перед
program.
мероприятием решили несколько расширить
Right
эту
before the
презентацию
event, we
и
decided to somewhat
рассказать не
expand
только
the scope
про
of my presentation
автомобили, про которые она
so
изначально
that I
была,
can
но
tell
и
you not
про
just
тех
about
людей, которые
cars,
это
which was my
движется.
initial
И в
intent, but in
частности,
fact
я
talk
сюда
about the
добавил
other
то, чем я
vehicles
сейчас
as well.
занимаюсь
That's
непосредственно,
why
это
I added here the
космические системы.
stuff I'm currently responsible
Что же
for,
такое
which is
киберфизические
aerospace.
системы?
Well, let me
Название
start by
скучное, но на
telling you
самом деле у
about
нас есть с чем мы
cyber-physical
встречаемся буквально
systems.
каждый день. В первую очередь это машины.
It certainly
Это то,
sounds
с чем мы
boring,
будем
but we
встречаться в
actually see
ближайшем
those
будущем
cyber-physical systems every
непосредственно,
day.
это
I'm
роботы.
talking about cars
И
here, but
это
also
то,
there will be
что
robots
летает.
entering our lives more and
Летают
more,
самолеты и
as well
летают
as
над
stuff that
системами,
flies.
что потрогать руками мы
And
не
here I'm
можем.
talking about
Это картинки,
planes and
кстати
satellites.
говоря,
The
я буквально в
satellites we can
прошлую
rarely
субботу
touch.
вернулся с космодрома Плесецк. Мы запускали
Now, I came
очередной
back from the
космический аппарат.
Plisetsk
Запуск был
from
успешный,
Plisetsk last week,
и
where we
зрелище
launched
запуска это
more
просто
units of
потрясающе.
ours. And you know what?
Люди
Observing the
хотя бы раз в
launch
жизни на это
is
посмотреть.
incredible. My recommendation is that
Что
you
из себя
try it at least
представляет
once in
киберфизическая
your life.
система? Ну, из
Now, what's
названия
a
в целом
cyber
может быть
physical system?
понятно,
As the name
что
suggests,
она состоит из двух миров. Первый мир
a
это
cyber physical system
физический
represents
мир,
two
то,
worlds. One is the
чего мы
physical
касаемся
world,
руками, там руль машины
the world
является
which is sort
второй
of
физический
tangible,
мир,
like the steering wheel of your
и
car belongs to
то,
that
что
world.
этим физическим миром управляет, обычно называется актуаторы.
And the stuff that
Эти
manages this world
актуаторы
is often called
управляются,
actuators.
соответственно,
Now, these
электронным миром. Мы
actuators
его с вами
are
привыкли
often
называть
linked
цифровым
to the
миром.
electronic
В этом
world or the
цифровом мире
digital world,
присутствуют так
as we
называемые
often
блоки
call it.
управления. Это уже
And there are
цифровые
control
устройства,
units in that
привычные
world.
нам,
So
не
these are
совсем
usually
привычные. Оно
digital
тоже
devices.
корпоратный
Some we are
блок, но тем не
comfortable
менее
with, others
он
not.
цифровой. К
But what
этим
matters is
блокам
that they're
управления
digital.
электронным могут подключаться
Now, these
системы,
electronic control
которые
units
реализуют алгоритмы
can
автоматизации.
be
Это уже полностью
connected to
автоматизированная
various
система.
automation systems,
И
which
все
makes
это нужно
our
запитывать.
system
Если это машина, то
automated.
источник
And
энергии
then it
это,
all
например,
needs
зарядная
some
станция. Если
energy.
это
So
космический
for a
аппарат,
car, it would
то
be a
его
charging
крылья, которые
station,
не
while
раскрывают,
for a
это и есть
satellite, it would
источник
be
энергии.
solar sails.
И как раз цифровой мир, либо мир
Now,
электроники,
the
это и есть
digital
тот
world or the
самый
electronic world
векторы атаки, которые присутствуют
is replete
и
with attack
используются
vectors.
атакующими для атак этих систем. Система, которую я сейчас показал, она больше
Now, the system I've just
концептуальная, она очень
shown
простая. Настоящие
is
системы
pretty
выглядят
simple. Real systems
они
will look
очень
like
сложные,
this.
там внутри очень
They're
много
incredibly
физических элементов
complex.
и
They consist of so many physical
этих
elements,
электронных блоков.
and they
Это
also
очень
include
сложная
over
система.
100 electronic units. So, like I said,
Но
they're
так было не
incredibly
всегда.
complex. However, it has not always
Они тоже
been this
подвергались
way.
эволюции. Вот
You
на
know,
примере
they've gone through
автомобилей
some
можно посмотреть,
evolution
что
of their
происходила
own.
эволюция. То есть
Look
в
at cars, for
50-х
example.
годах
You
этих
know, it
электронных
shows their
блоков было
evolution.
совсем
So in
ничего.
1950s,
Но в
those
настоящие
electronic
годы
units
этих
were
блоков
very
возросло там до
rare.
сотни и больше.
However, the number of these
Появились
electronic subsystems
высокоскоростные
has
товарные
pushed
связи
the
тоже
threshold
внутри
of 100 lately.
И вся эта
Now,
эволюция
inside
связана с
those
тем,
vehicles, we're
что
also
мы будем
finding now
потребители
high-speed
хотим все больше и
comms,
больше
which is
сервисов
natural.
получать от этих
As users,
физических
we
систем.
want to get
Поэтому
more
они
and more
в очередь
services from such
Но
physical
вот этот
systems.
уровень
That's why
сложности, естественно,
they
никому не
evolve.
нравится, потому что
Nobody
чем
likes this
сложнее
level of
система, тем
complexity,
больше
though,
вероятности в ней
because the
ошибок,
more complex
тем
your system is, the higher will be
более
the probability of
вероятно эти
error.
ошибки не найти.
And at the same
Поэтому
time,
вся
it
эта
will be more
индустрия, в том
difficult to
числе,
discover
кроме
those errors.
усложнения
So the
архитектуры,
whole
она
industry
идет
is going
по пути
towards
упрощения архитектуры.
a more
И
complex
эта
architecture,
архитектура
but they're also
постепенно
trying to
эволюционирует
simplify
к
the architecture. And this
Здесь можно
architecture has been
посмотреть на этой
evolving
картинке. Не очень
towards an
понятно, но тем не
IT-like
менее вот два
architecture.
таких
It may be difficult for you to read this
голубеньких
particular
квадратика
chart,
это
but note
условно
the
два сервера.
two blue
И
squares
вот
in the
все вот
center.
эти
They're like two
электронные блоки,
servers.
которые стоя сказал,
So
то
all the
есть все
electronic
идет к
units,
тому,
remember I
чтобы
mentioned
машина
100 subsystems.
превратилась
So
в
effectively,
систему, в которой стоит два
the
сервера,
car
и к
of the
этому серверу
present
подключены
has two servers,
вот
and
эти
connected to
физические
these
элементы.
two servers are all
И
these
есть
physical
дополнительное такое
elements.
целое направление, называется Software Defined
So
Everything.
there is this
И тоже
whole area
Software
called
Defined
software
Satellites, Software
defined
Defined
everything,
Vehicles, Software
SD
Defined
satellites,
Robotics.
SD
И вот здесь как раз
vehicles, SD
нарисовано, что вот эти вот
robotics.
маленькие электронные блоки,
And
которых очень
as
много
the
в
illustration suggests, those little electronic units, which modern
такой
cars have a
сервер
lot
блейдовый,
inside them,
где эти блейды
will
можно
turn
добавлять
into a
в
blade
зависимости от того,
server
какая
like this.
производительность вам нужна
So
и какой
you can
функционал вам
add
нужен.
more servers if
Ну
you
и,
need extra
естественно, сверху
functions or high
возникает целый
performance.
стек
And on top of that, you have a whole stack of software to perform the functions that a particular physical system will need. Naturally, you cannot do it without Kubernetes, right? Now imagine you're driving your car and you have Kubernetes running under the hood of your car. Isn't that scary? Now, these systems are architecturally special, but in terms of development, they're also quite unusual. Shown here is how such development is done. Now, it consists of a pretty long supply chain. So, shown here are different suppliers like Tier 1, Tier 2, OEM obviously is the car manufacturer. So what you see at the bottom is a microcontroller, and it gets soldered to a circuit board produced by some other company. Then they assembled into a subsystem coming from yet another supplier, and then this subsystem goes into the vehicle, and the manufacturer is the name you can actually recognize. When I found my way into the automotive industry, what became a total revelation to me is that a classic car manufacturer does not write a single line of code. They're effectively engineers, or rather configurators. They buy everything they need in the market and they put it all together. That's like a horrible waterfall. This waterfall is then broken down into these subsystems, and the level of complexity that goes into these requirements is mind-boggling. So the CEO of Ford, talking about this level of complexity, once said that they have over 150 modules produced by over 150 different companies which never talk to each other. So it's not really clear how this whole stuff works. And this makes us think of something like this, right? These systems are very complex. So, they often connect different elements and they see that they do not connect. So their waterfall project management should probably go through 4, 5, or 6 iterations, depending on their quality requirements. And every iteration lasts for like a year, which means that such systems take like forever to develop. Now, all this naturally means that attacks are also evolving. As architecture gets simpler and more functions get developed, and the development system is complex, it's not surprising that we're seeing more and more attacks. Now let's look at the evolution of such attacks. Now, everybody remembers 2007 and Stuxnet attack versus industrial systems. So we often say that that was the start of attacks targeting cyber-physical systems. 2015 saw the well-known hack of a Jeep. Now that meant that the Pandora's box was thrown open. In the automotive industry, pretty much nobody ever thought about security. That was indeed a veritable Pandora's box. They've been driving this box since then. They, I mean hackers and security researchers. Now, there have been numerous attacks since 2015. Some of them included real ones. Others were more along the lines of research. And sometimes you may think, well, they must have invented all. They couldn't be serious about it. So in 2024, they did a supply chain attack at, targeting Zeekr. So in this video, they're just, shooting it all. As I was watching it, I was thinking to myself, now these people are courageous. Well, because you don't really know what they have hacked. Like in a car, so many things can go wrong, and the consequences can be horrible. Now in 2022, we started seeing public attacks targeting satellites. Now, this is something that we are seeing even here. The current festival is looking at the space industry as well. Now, in 2023, at a Black Hat, they first showed how they could hack satellites. Well, they were mostly looking at CubeSats, which are kind of student satellites, mostly developed as part of some university programs. And for the first time, US government did a kind of a bug bounty, or they invited hackers to hack their satellites. Now, that happened in 2023. What happened in 2022 is that Viasat got hacked. That was 2022, a legendary year. So Viasat came to Black Hat. They shared some details. They didn't tell us much, but if you can read between the lines, good for you. If not, you can get in touch with me. I'll be happy to share the rest with you. So they bricked land-side infrastructure, and some of the satellites were also bricked. Okay, threat actor model. Who are the people doing those attacks? Why is it important to know about them? As an InfoSec person, I'm just like that. I usually feel too lazy to give a damn. I'm usually thinking like, well, we'll just secure it. You do it well, it will work nicely. It doesn't work this way. Remember the electronic control unit I showed? If you harden it, if you secure it, it will be like 10 times more expensive. Now imagine that it's not just one, but you have 100 units like this. So being serious about security, you can just kill your product. The bill of materials can easily get 10 times bigger.
Поэтому именно здесь, в рамках киберфизических систем, вам придется это делать.
For cyber-physical systems, you will have to perform this exercise. You will have to develop your threat model, not because the regulator says so, but because otherwise you won't be able to develop a common language with developers and business people. Before you develop the architecture, you need to answer the question of who the attackers are. The most important question is, who is your physical attacker? Because when you put your physical system on the market, you'll no longer have access to it. So what's going to happen to it in the field, you'll probably never know. So please consider who is going to attack which systems. Now, let's consider a particular automotive example. Unfortunately, I cannot tell you much about satellites, but what I can share, I will. Now, this is a threat actor model for the automotive industry. In the inner circle, you can see attackers which will be very interested in attacking the car. Obviously, it's a thief, a service engineer, but also the owner, surprisingly. And I'm also putting APTs here. I'm doing it since 2022. Now, the rest is like the environment, which doesn't really depend on the kind of product you have. Oh, right. And there are also, well, not very different from APTs, right? But like law enforcement agencies. But, this makes a lot of sense for satellites. What if it's, our side, Russian law enforcement? It would be even funnier. Now, this is actually a real-life example. And what you see here is a shortened version of it all. So these are just cases like doing a jailbreak. So we have some scenarios here about thief, for example, stealing the car. Well, if he uses a towing device, a towing car, whatever cyber defenses you build, it won't help you.
На примере машины можно сформулировать физические
Now we can list some physical targets, or rather physical objectives you would want to achieve in order to harden the security of the car. Now, if you're going to do something like this, I suggest Stride for cyber-physical systems. Stride is a great fit. You can find templates online, you can apply. You like it. This summer, Mitter promised to publish their methodology for embedded devices, and actually the control units I previously mentioned are embedded devices. So this way, we'll have something, we'll have a good reference to consider or to consult. There are also various adaptations, for cars, for satellites.
Теперь про архитектуру. То есть по поводу контекста мы поговорили.
We've discussed the context already.
Теперь про архитектуру. В первую очередь, так как у нас все-таки про хакеров, да, то...
Now, since the whole event is about hackers, let's talk about cyber resilience. Let me remind everybody what that is. Because some people use this term all the time, others do not. But I find it quite important.
Что первая задача, или цель, можно назвать, которую преследует...
Now, the first objective we pursue is cyber resilience, second one is monitoring and response, and the third one is restoration. So the system you are developing should ideally be good on all the three counts.
Пойдем сейчас последовательно. Первый — это...
And this is the order that we shall follow. Let's talk about defenses. Now, these are the layers of security architecture of a cyber-physical system, and they're not really different from the architecture you'll see for other systems. However, as you analyze the lower layers, such as physical protection or electronic control units, you will discover that as a developer of software, you'll have to think about them. Usually you're sort of aware that there is a physical layer, but you don't consider it as such. In Europe, the legislation has got developed so much over the past several years that the regulators have nudged the automotive industry to develop proper standards for cybersecurity. So in this respect, European automotive industry is quite mature in terms of InfoSec. So they've got all sorts of solutions and specifications you guys may want to use as well. Now this picture shows how you can analyze those different layers, kind of cascade them to the level of functional requirements. I'm showing it here to illustrate the following point. Shown in green are the elements that an automotive manufacturer, a classical one, can effectively control. Well, because they have a long supply chain, don't they? And there is IP associated with it. And even the OEMs, they are not getting this IP. So quite often, OEMs are getting kind of black boxes from their suppliers. They cannot control what's there. They sometimes won't even know what's there. Well, there is obviously the neo manufacturers, the neo car makers who are trying to address this problem. Like they take some of the key electronic units and make sure they control them. So the white stuff in the previous charts, which is effectively an InfoSec set of holes, they try to address. A rival was like this. And Atom, a Russian car manufacturer, is also trying to do something similar now. So they can be considered neo-manufacturers, neo-car makers. Now let's talk about security of electronic units. I think it's important for you to understand what the issue here is. That will tell you why you should care a lot about the other units. So this is what it looks like. Like I said, in a modern car, you will have over 100 units. For Ford, it's more like 150. Tony Chen from Microsoft made this report about how they defended their Xboxes. Now, the short excerpt from it is like this. Producing a system that's secure from physical attacks, leveraging easily available components is not exactly impossible, but extremely difficult. Now, those whose business depends on it, such as PlayStation or Xbox, they develop custom chips or custom systems on chips. to provide better security. In the automotive industry and other cyber-physical industries, this is even worse, because the electronic components, which you need to buy for them, for purely operational reasons, have to meet strict requirements in terms of temperature and what have you, or if I say vibration. They certainly need to meet much stricter requirements than the stuff you're simply going to put on your table. So, hardening a unit of a cyber-physical system can be quite difficult. So, you do need tiered defense. Absolutely, it's a must. Have you modeled your perpetrator? So it's very important to understand who can potentially attack your stuff and why. Now let's look at a hardened electronic unit. We usually call this way units that have the so-called HSM. Everybody calls it HSM, though it's a misnomer. They're sort of seeing it through pink glasses. It's more like TEE, Trusted Execution Environment, something you have in your phones. So there is a separate core running separate firmware, which is shielded from application cores. It has its own storage, which again cannot be addressed, so to speak, by the application cores. And this way they can do safe loading, safe startup. Now they can also store some cryptographic primitives there, and they can store the keys. Now, what's the issue with it? Now, the chips they use for it, they are not certified by anybody. They were not designed to address a particular threat model. They simply meet some specs. And the same is true for those who develop, say, firmware or software for those shielded cores, which means that the actual level of protection seems to be below the keystone. And still, they need to be secured, and we need to be serious about the specs. It's a hygienic requirement, isn't it? Now, the security of such electronic units, if you are not planning to attack them physically, like who is going to attack the control unit you use to lower the windows in your car? Few people are interested in that, right? But they also introduce some security, and it's more along the lines of quality, right? The better quality you build into it, the better you test it, the more secure it will be. So it's not really HSM, please remember it. Also, implement embedded secure elements, or TPM, where you need better protection against physical attacks. It's also extremely important to work with your supply chain. I have already mentioned that supply chains are long, so what you see here is a checklist for dealing with the suppliers. I won't stop here, you can read my presentation later. I'm short on time. Physical protection, why is that important? Now, physical protection, or job subject, now there is this notion of window opportunity, which describes the amount of time an attacker has to mount the attack. Now, physical protection enables you to shorten this window. There is the alarm built into it. There are some physical elements that will get in the way of the attacker trying to connect to the internal networks. And all this is designed to add another tier of defense or protection to the electronic units. So in my presentation, I actually provide more details about how car makers trying to prevent car theft. So the electronic unit should be shielded in a way so that the thief cannot disconnect it within 2 minutes. So it's like a very clear-cut KPI for that. Now let's look at a classic network. Let me remind you that the landscape is complex. At the same time, the network is still your regular computer network. You've got some electronic units, you've got external interfaces, and these interfaces are exposed to the outside world, but there are also some private units. So you need a DMZ separating them. And you also need to do access controls, you got to do your firewalls and so on. However, these networks have gone through an evolution of their own, and I still remember the type of networks which are shown here as belonging to 2010. That looked like a bit of chaos. Defending anything there was almost impossible. So then, InfoSec legislation got adopted, and the level of complexity of course went up. So we saw some, sensible evolution, and eventually star-shaped arrangements developed. So the next stage naturally is domain centralized or domain controlled. It looks like a central computer here. It looks like servers with blade servers. So fortunately, architecture has now arrived at the stage of a central gateway. And now it's clear for us where to install the firewalls and how to delineate accesses between different network segments. Now let's look at specific examples. That was a rival network segmentation some time ago. With this network layout, and yes, you will see that it looks like domain architecture, but with a twist. Now, the issue they tried to address here was that of plug and play, because they needed to connect controllers in sort of arbitrary order, depending on the physical architecture of the car. Because of that, all the systems that had external interfaces, they would already have those domain controllers on board, and that domain controller was effectively a firewall as well. So it was a self-sustained unit. You could plug and play anywhere, and it wouldn't do any harm to the car. Now, this is a different architecture. You see the central gateway here, and you see below and above security gateways. That's a different architecture, which I personally believe to be better protected. Actually, Atom is currently following an architecture like this. So this security gateway separates everything into trusted and untrusted worlds. Now, this concept came from trusted execution environment, the hardware world, so to speak. What's interesting about it is that it really clearly shows the boundary between the trusted world and the untrusted one.
Переходим уже к следующему блоку киберустойчивости.
Next one is monitoring and IR.
За счет того, что автомобильная индустрия, как я сказал, забежала довольно вперед,
Since the automotive industry has made great strides lately,
intrusion detection system. Они есть как хостовые.
Cars have intrusion detection systems. Some are host-based, others are network deployed. They can be embedded in functional units, or they can be supported by individual network elements. They know how to collect anomalies and send it all to Vehicle Security Operations Center. And there was a well-known case in Europe after which they started doing vehicle SOCs.
У нас в России тоже сейчас только начинается инициатива по созданию такого Security Operations Center.
Creation of such a Security Operations Center is in its embryo stage right now. The problem is that we do not really have the right legislation for that, so it's not happening fast. What's peculiar about this intrusion detection is something I'm trying to illustrate here. If an attacker connects some device to CAN, and it's a passive device, you won't be able to see it. Not a single intrusion detection system will see it as long as this device does not generate any commands. When it does, it may be too late. There is a separate type, therefore, of voltage-based intrusion detection system, and this is what Mercedes is doing. So, if a device gets connected to CAN, because of VITs, the car simply won't start. So when people talk about intrusion detection, the first question that comes up is, how do we react? Imagine that a Tesla car is attacked by a drone. So the car has a state, and this state currently is called stationary. The car is considered safe. It's pretty difficult for this car to harm anybody at this moment. There is a different state called drive. You know, when the driver gets in the car and starts driving, imagine, the drone is following the car, you accelerate 250 kilometers per hour, and, the drone accelerates to the same speed, and then it starts, say, opening the doors of your car, or starts braking your brakes or braking your car. What's interesting is that when we talk about those intrusion detection systems, by the way, we are afraid of using prevention in the real world, but here it would be even scarier. Maybe hackers do nothing and you've already wrecked the car because you triggered the intrusion prevention system on. That's why in the automotive industry, they tend to be very, very careful. The general consensus is that, they will lower the speed, and they will try to take the car closer to a state where any attack will not create harm to the driver or anybody else. Now, in satellites, you can disconnect whole domains inside the satellite. So if you see something anomalous, you can switch a whole domain off and set the whole satellite to compromised state, and then start the restoration process from a trusted area. Now let's talk about restoration or recovery. I see that my time is up. Shall I finish? Do it fast, okay. Now, if you do no restoration, well, it's pretty difficult with the satellites, It's difficult with cars often. Like if your car has been bricked, you tow it to a service station, and that can easily cost a lot of money, which means that we gotta consider restoration and recovery well in advance. I've got a checklist here. You can read it on your own.